Good morning. All right. So we've got a couple of homeworks on the horizon here. Homework 5A is due next Tuesday, and then homework 5B is due the following class period. In the past, I used to combine homework assignments together, and so you may be wondering, like, why A, B, C? When I first started teaching, I just had one homework assignment per chapter, and it ended up being like a big thing all at once, and I found over time that students seemed to do a little bit better when I carved it into more manageable chunks. It's just that sometimes those manageable chunks line up that it's back-to-back submissions, and so this is going to be one of those where you've got an assignment due on Tuesday and Thursday, but it could be worse. It could all be due at the same time. So. Today we're going to be continuing talking about Chapter 5, the continuity relationship, and one of the specific applications of that is the Reynolds transport theorem. So before we get into that, are there any questions related to the announcements or related to the lab that we did yesterday? Okay. In class last time, we did a couple of examples where we ended up saying that inside of some control volume, the accumulation is the difference between the in minus the out. And so what we were looking at is we were looking at flow in and out of a control volume, abbreviated CV. Remember that the outside surfaces that encompass that control volume are the control surfaces. So the surfaces through which the system flows. And we defined the system as a continuously connected mass of particles. And it's the same stuff. So the system may be oil, it may be water. The system may be something that's suspended in water. The system could be some pollutant that's suspended in water. And what we said is that if there's no reaction, then the accumulation inside the control volume is the difference between the flow in and the flow out. So let's look at that in more detail. This Reynolds transport theorem says that there can be an accumulation of mass over time if you keep track of the difference between the in and the out, and there may be a reaction going on inside of the control volume. In a lot of cases there is, especially for those of you in environmental engineering this semester. You're learning a little bit about reaction and kinetics. But these two terms of the Reynolds transport theorem can be broken up into a storage component and a transport component. The storage, if we look at this, what we're saying is that there is an accumulation in the control volume of mass times a change in volume over time. Now this V with the cross through it, that means volume, whereas this V we're using to represent velocity. So velocity and volume. In the case of the storage term, if we multiply the volume by density, then that's how we're getting some system mass. Remember that the continuity relationship can be expressed in terms of volumetric flow rates or mass flow rates. Now mass is always conserved. Volume usually is, but not always. Think for instance with a compressible gas. We could have a compressible gas entering a compression cylinder, and the volume of gas that comes in doesn't necessarily have to equal the volume of gas that goes out if the two gases are entering and dispensed at different pressures. So volume is usually conserved if we're talking about liquids, but mass is always conserved. And that's why the Reynolds transport theorem is being expressed in terms of mass. We're saying that the mass's change over time is related to the accumulation in the control volume, so some change in volume. The dV means that the volume can increase, it can decrease, that amount stored inside the control surfaces can change over time. And then the transport term is saying, let's keep track of the fluid density, its velocity in or out, and then the cross-sectional area through which it's passing. And so this dA is the portion of the control surface that the fluid stream is going in and out. And inside the transport term, there can be multiple streams. The example we worked for Oahe Dam at the end of class on Tuesday was there was 2 streams coming into the reservoir, 1 stream going out. And so although it's just a single term in the equation here, the transport term can have multiple ins and outs that we have to account for. And so this is the net of all of that transport. So remember, these are all of the same variables that we've been assigned so far, with the exception of, I'm not sure if we've used this v with the cross through it to differentiate between volume and velocity. Usually you can tell just from the context in which it's used. But here it's explicit since both appear in the same formula. So this Reynolds transport theorem is relating the rate of change of a property to the rate of reaction inside of the control volume and the rate of transport. So remember, some properties are related to the mass of a system. And most specifically, the one that comes on our radar pretty soon is the property of momentum. And so momentum is proportional to the amount of mass you have. Other properties are independent of mass, things like color, viscosity, the inherent properties of the fluid. Okay, now in this class, we're going to assume that there's no mass being created or destroyed in the control volume. And in other words, you can worry about reactions in 351, but here in this class, we won't worry about reactions quite yet. So we're going to assume that this dm dt of the system's change over time is 0. So there's no mass created or destroyed. And so what that means then is that the rate of accumulation is entirely described by the difference in the mass flux in and out through the control surfaces. So this storage and transport term is the sum of it is equal to 0. So that means that if the liquid level in the storage volume is increasing, that must mean that there's more in than out, and vice versa. So this is just another way of simplifying this expression, and it's kind of related to what we looked at in class on Tuesday. We say that the change of mass in the control volume over time is equal to the mass flow rate in minus the mass flow rate out. So accumulation is in minus out. We're just kind of generalizing that onto a mass flow basis. So we have units of time here. So this is the Reynolds transport theorem, and it can be applied in a lot of ways. One of the ways that we can use the Reynolds transport theorem is to use formulas that apply for conditions along a streamline. Remember, we've emphasized several times that Bernoulli's equation should be applied for an inviscid fluid that's incompressible, steady flow. But then there's this, one of the assumptions is that it's along a streamline. And so the Lagrangian approach says that you need to track the trajectory of every particle in your system if you want to have a full and complete understanding of all of the velocities, the pressure changes. This Lagrangian approach says let's keep track of streamlines. So to find the pressure at B, if that's the question, we're given a decreasing diameter of a pipe, and so we know that the velocity was slow at A, and because of that changing cross-section of the area, since it decreases, the velocity has to go up. So to find the pressure at B, one approach would be to integrate Euler's equation as the particle moves from one location to the other, or just to apply Bernoulli's directly if we have steady flow conditions. But the problem, as we've discussed before at the beginning of chapter 4 when we talked about flow visualization, remember the problem is keeping track of all the particles. And so rather than trying to do that, rather than trying to keep track of the position of every water molecule as it travels through a transition like this, it's easier to divide the transition up into elements, into little cells. And then what we do is we apply these equations like Euler's equation or Bernoulli's equation, we apply them at the level of the mesh. So that means you can develop a solution that provides the flow properties at any point by applying the free body approach. And we say that the properties of the fluid get transported through this control volume. And so the fluid's momentum, the fluid's velocity, its pressure can be looked at on a cell-by-cell approach, and we look at what flows in and what flows out, and then how is it changing inside of a smaller cell. And the more resolution that we have, the more accuracy we'll enjoy when trying to find the pressure at location B in this pipe. So we would track the pressure and shear stress forces that are acting. And so one of the purposes of the Reynolds transport theorem in fluid mechanics is to allow us to apply these equations that we say, well, really it'll never apply in reality, because none of those assumptions can be fully satisfied, not all of them. You know, we can have a gas that's fairly inviscid, but then it's highly compressible, or we can have a liquid that's pretty incompressible, but it has a high viscosity and therefore is going to experience energy losses. You know, these equations are really elegant and they're beautiful, but they don't apply as easily as we'd like because of friction losses and because of the fact that we're not always applying them along a streamline. So the Reynolds transport theorem kind of is a solution to those problems. Okay, so let's get some more experience with this idea of keeping track of flow in and flow out, the continuity principle. Continuity meaning that the mass has to go somewhere. If we have mass coming in through these control surfaces that are defined, and inside, encompassed by the control surface, is a storage area, like this tank, how is the fluid level changing over time? In this case, what we want to know is the velocity of this liquid level. You know, is it going up or is it going down, and at what speed? And what we're often given in problems of this type is we're given some flow in, and you can see here it's defined as the average cross-sectional velocity and the cross-sectional area. Looks like it's being poured in from some other container. And then the liquid is leaving out of the bottom, and this is not a free orifice. So this is different than what we saw in the lab yesterday. You know, in the lab yesterday we had a jet coming out, and the flow out of the jet depends on the liquid level height. The two clues that this isn't one of those problems is, number one, it's a pipe that's coming out. And so you can see that thick black line on either side of the liquid. If it was instead an orifice, then what we'd have is it would try and look like some streams or ripples, and there wouldn't be the thick black edge on the side. The other thing, the other clue that this isn't a free orifice is that we're not given any measurement from the liquid surface down to the opening. And so this is a regulated outflow, and it's given in volumetric terms, 0.003 cubic meters per second. So this is water, which means we can use the typical density of 1,000 kilograms per cubic meter. We can turn this volumetric flow rate into a mass flow rate, and you can turn this velocity and area into a mass flow rate. But what we're trying to figure out is how quickly the liquid level is rising. So that's actually a volumetric question. If we look at this tank in a little more detail, in the problem statement it says the water tank is circular with a diameter of 0.50 meters. That means the tank looks like this, 0.50 meters. Okay, so we want to find out, is it going up, is it going down, and how fast? You're going to need to calculate the cross-sectional area of that tank, because if it's a really big tank with a large area, then the net difference between the flow in and the flow out would mean it falls or rises relatively slowly. Has anybody here ever tried to fill a pool before, a swimming pool with like a garden hose? It takes a long time. You get really bored waiting for the pool to fill up with a garden hose. And that's because it's a big cross-sectional area. So the speed of the rise and the fall is going to be kind of a Q accumulation that you'll solve for. So I don't want to say too much more of it besides that, because I think there's some intellectual jumps you can make in solving this. But what we're trying to figure out is how much mass or how much volume is accumulating in the control volume over time. So what's the net difference between in and out? And once you find that net difference, it'll tell you if the liquid level is going up, going down, and you can calculate the cross-sectional area to tell you the velocity. Okay, so is the liquid level, is it going up or is it going down? It's going up because there's more coming into that tank than is exiting. If you do the calculations, you find that there is, let's see, on a volumetric basis, 0.0175 cubic meters per second flowing in. And if we convert that to mass, it's 17.5 kilograms per second in. And the out is 0.003 cubic meters per second, and the mass basis says 3 kilograms per second. So the net difference between the two is 14.5 kilograms per second. So that's the rate that mass is accumulating inside of there. So the liquid level is increasing, and the speed of its increase is going to be 0.0738 meters per second if we consider the cross-sectional area of that tank. So we know it's rising because there's more in than out, and the V rise, as I call it, it's just a Q equals VA kind of a thing. And it makes sense that if the tank area was bigger, then the velocity that it's rising would decrease. So if this number in the denominator was doubled, for instance, then the velocity that the liquid level is going upwards would be cut in half. So later on in the semester, we're going to be talking about, actually it's next semester in hydraulics, we'll be talking about tanks that are used to prevent surge associated with water hammer. And one of the strategies is to put these intermediate storage tanks in a long water pipeline so that water can rise and fall in the storage tanks rather than cause increase of pressure in the pipe. So you'll revisit this idea of the velocity rising, and you'll try and calculate how big in diameter a certain tank needs to be to limit the V rise to a certain rate. Yes?
So when I did it, I didn't convert the flow rates to mass.
And that's fine. Yeah. Yeah, you know, I asked you to convert it to a mass basis just kind of to reinforce in your mind that m dot is Q times density. But you're right, you don't have to, as described, you don't have to solve this on a mass basis. You could have just gone volumetric. So you may notice that I just changed the example so that in future semesters they'll be forced to do the mass flow rate and not feel like they wasted their time. But anyways, good point. Are there other questions about this example? All right. Well, let's move on with another application of the same idea. Now, we have a reservoir that has a couple of pistons, and the piston on the left, piston A, has a diameter of 3 centimeters, and it's sliding to the left at 2V. So we don't know the velocity, but we know it's going double the velocity as piston B. So piston B is moving to the left, so that's forcing flow into the tank at V. And piston B has a diameter of 6 centimeters. So we have flow in, and we have flow out, and then we have a control volume, and what we're interested in is the water level in this control volume. So consider it for a moment. Flow in and flow out, a liquid level. So what's happening to that water level inside the control volume? In the tank, is the water level steady? Is it going up? Is it going down? How are things affected by those two pistons? Who thinks that the water level is going to be going down? By the way, you have to vote. Everyone has to vote. No conscientious objectors in this one. Who thinks the liquid level is going down? Okay. Who thinks the liquid level is steady? Who thinks the liquid level is going up? Boy, it was maybe a third for each one of them. So what we can do is even though this is symbolic, even though the velocity is symbolic, we can apply this same Reynolds transport theorem idea and find out, is the mass positive or negative in the control volume. So what we can do is, remember, this is water, and so density will be 1,000 kilograms per cubic meter. 1,000 kilograms per cubic meter. And then we're going to have some area and some velocity. And we can have the velocity just be as the variable v. So what is the area at A versus the area at B? So the area at A is going to be pi d squared, and so the diameter is 3 centimeters squared divided by 4, whereas the area at B is pi d squared, where d is 6 centimeters divided by 4. Okay, so that is area A is 7.069 centimeters squared, and area B is 28.274 centimeters squared. Does anybody want to change their answer? Are you seeing the trick of this question? This question is constructed specifically to trick you, to make you think, oh, the liquid level is going to stay the same, because like the trick is, it's got double the velocity at A, but half the diameter. But the flow rate isn't dependent on the diameter, it's dependent on the cross-sectional area, right? So although it has half the diameter, it has 1/4 of the cross-sectional area. Do you see what I'm getting at? If we look at now the Q in versus the Q out, so flow in, the flow in, Q in, is V in times the area at B. And so that's V times 28.274 centimeters squared. So let's just call that 28.274 V. That's the flow in. Flow out, Q out is going to be V out times the area at A. So the V out is 2V, and the cross-sectional area is 7.069 centimeters squared. So that's 14.138 times V. So now, let's put it into a mass basis. I should have maybe started a little higher. We can write dm in the control volume dt is density times Q in minus Q out. So what I've done is I've just rearranged the mass flow rate. I can take the density term out of both the in and the out, and so that's why it's on the outside there. So it's going to be density times 28.274 V minus 14.138 V. So the net is 14.136 times the density times V. So that's positive. That means that the mass inside the control volume is accumulating in a positive way. So what's going to happen to the water level? It's rising. So in other words, there's more going in than is going out. Any questions about that illustration? Just reinforcing that cross-sectional area is a function of diameter squared. So we can apply the Reynolds transport theorem even when things are symbolic. If we don't know the absolute velocities, that's still okay. We can use it to figure out whether there's a net accumulation or a reduction of mass in the control volume. Okay, this is one of my favorite examples of the semester. I really love this one. It looks tricky, but it's deceptively easy if you pick the right control surfaces. So this is a continuity problem, and what it's saying is that we have some tube that's full of water. So we've got this tube of water, and a circular cylinder is falling downward through the circular tube. And so if we looked at it from above, let me draw a little sketch of what this scenario would look like. Okay, so if we looked from above, we'd have this outside tube that's full of water, and it has a diameter of 0.20 meters. So that is the diameter of the tube. And then in the center line of that is this cylinder that's falling down. Now what happens as that cylinder falls downward, the water has to flow out of the way. So think about, as it moves down, as that cylinder moves down, it's pushing something out of the way. It's displacing water. And the water can't go down because this container has a hard bottom to it. So as the cylinder goes down, it's not compressing the liquid because this is water, it's incompressible. Instead, it forces the water to go around the outside. And so, you know, if this solid cylinder moves downward at such a rate that it displaces a liter of water, then that liter of water has to pass upward around the outside edges. So does everybody understand that in 3D? What we're saying is the cylinder goes down and the water goes up. So the continuity equation here will allow us to find out the velocity, the mean velocity of the water in the space between the cylinder and the tube wall. So how fast is that water moving when it is here, in between the cylinder and the tube? Okay, so the suggestion that I give you is on the notes if you've got them, or you can do a sketch on just a scratch piece of paper. Try and sketch where the control surfaces should go. You know, what we're saying is accumulation is in minus out. Well, inside this tank, there's no place that fluid can accumulate beyond where it already is because, you know, it's full, and so in equals out in this problem. The Reynolds transport theorem, what we're saying is you sketch a little control surface where you've got mass coming into the control surface, mass going out of the control surface, and that approach will allow us to determine the velocity through the control surfaces. So I'm going to pause for a minute. This is a head scratcher trying to figure out where to put the control surfaces, and just as a hint, a good spot to put them is where things are moving. You know, the real control surfaces that dictate what's happening in the system is where is something flowing in and where is something flowing out. All right, I'm going to give you a minute to think about this and discuss it with your classmates, and we'll see if we can find the velocity of the water in the side space. Tricky, right? I mean, it ends up being an easy problem, but when you first look at it, you're not quite sure exactly what's going on. Okay, so let me have you pause for just a moment before you get into the number crunching, and let's make sure that everyone can visualize what's happening. So the cylinder's falling down, and as it falls down, it's pushing water out of the way. So I've drawn some control surfaces here. And what I'm saying is if the cylinder enters, if it falls down a certain amount, like if the cylinder goes down to here and is occupying that space, then the water that used to be in that space has to go out of the control volume. So even though the cylinder is a solid, it still has the ability to displace liquid. So we can apply this Reynolds transport theorem on the volumetric basis to both solids and liquids, because the solid entering the control surface is displacing the liquid out the side. And so you're going to use kind of the same idea that you did in the last problem, where we're going to have some velocity. We're going to say like the velocity out is the Q out divided by the cross-sectional area through which the fluid is flowing. So here's the tricky part, is determining like what is the area that the water is going out of that control surface. So I'm going to pause again after having shown you what I think the control surface ought to look like. And what we're trying to do is we're trying to find out what is the velocity of that liquid that's going out of the control surfaces. So this is the V is what? So the concept is that the cylinder falls down into the control volume and it causes the water to squirt out through the sides. So why the sides? Like, why isn't the water going down out of the control volume at the bottom? Well, because the container has a hard surface at the bottom. It's got no capacity for storage in there. It can only flow out through the sides. It can't go sideways because of the pipe. So it can only go up around the edges. So you calculate the flow in based on the velocity in of 1 meter per second, the cross-sectional area of the cylinder. So that cylinder, this volume, the Q in, what we're talking about is the rate at which the cylinder is entering the control volume. And that's going to be the same rate that water is displaced. Now there's no accumulation, so just the Q in equals the Q out. There's no place that the water can be stored in our control volume since it's already full. So you find the difference in the cross-sectional areas to find the net flow area. So the water won't be flowing up through the cylinder. The whole reason that water is displaced in the first place is because the cylinder is solid. So it can only flow up around the edges. So that's why we need to subtract the big cross-sectional area of the tube with the cross-sectional area of the cylinder. All right. So 1.29 meters per second. Does that make sense to everyone? All right. Very good. Yesterday we took a look at the orifice equation. And remember, the higher the liquid level got in that container, the higher the velocity of discharge was. So the height of the orifice dictates the flow rate, because as the water height increases, the pressure goes up. And it's the pressure that causes the liquid to accelerate towards the opening. The control volume can change with respect to time. And what we mean by that is that the liquid level can fall or it can rise depending on if there's a net increase or decrease in the storage volume. And we saw the orifice equation, and that's derived from Bernoulli's, where what we're doing is we're just saying in the jet, the assumption of this orifice equation is we're applying it between the surface and the jet, and since there's air surrounding that liquid jet in all sides, then the pressure at 2 is 0. the velocity and pressure at 1 are 0, so then all that's left is some height difference between the two, and that's what's driving the velocity at 2. So essentially h is the square root of, h is v2 squared divided by 2g, because every other term of the Bernoulli's equation got canceled out except for the elevation differences and the velocity head at 2. So again, just to emphasize, the height is measured from the center line of the orifice. We can apply the continuity equation here and the Reynolds transport theorem to say that we can keep track of the flow in and the flow out, and then from that determine if the liquid level is rising or falling. And in our next class period, what we'll do is we'll introduce an equation that allows you to estimate how long it takes for the liquid level to fall a certain amount. Because as the liquid level gets lower, the pressure decreases and the velocity decreases, and so it's a nonlinear relationship in time versus velocity out. And velocity out depends on the height, and you can see that it's a square root relationship. So we'll get into the specifics of that time calculations in the next class period. One application I wanted to point out of this Reynolds transport theorem is the sizing of a flow equalization basin. This is a diagram of a wastewater treatment plant. And wastewater treatment plants are a little bit unique in that wastewater is generated at variable rates during the day because people use water less in the middle of the night than they do during the daytime hours. Like if you just think about maybe around 8 o'clock at night when people are washing dishes and maybe doing laundry, taking showers, flushing toilets, there's a lot more human activity at night in the early evening hours than at the late night hours. And so this treatment plant has a lot of water coming to it sometimes and just a trickle at others. And since it's a biological process, the microorganisms that do the purifying of the water, they can't turn on and off like a light switch. They react actually very slowly, and so it's much better from an efficiency standpoint if they always have a more constant flow rate. And so there has to be a storage tank inside of a water treatment facility if you want to provide that attenuated flow. In other words, you've got these big swings in flow during the day, and it's better if the bugs just have some constant flow rate. And so what you do to dampen the variations in a water treatment plant is you provide some tank that is filling up during the day when you've got a lot of flow, and the tank is emptying at night. So consider this graph where it's below the average in those nighttime hours and above the average in the daytime hours. If we look at this, it tells us when the tank is filling and when the tank is emptying. If we're trying to always have the average daily flow go into the treatment system, then anytime the average daily flow is greater than, anytime the given flow rate for a certain time period is greater than the average, then you'd take any extra and you'd fill the storage tank. And then at night, you'd drain the storage tank. And over a 24-hour cycle, the objective would be to discharge into the treatment plant at night all of the stuff that you'd stored during the day. So sizing of ponds doesn't just apply to wastewater treatment plants. It also applies to stormwater from developments like the new Tanyard Station development that they're doing over on Route 60. That used to be an undeveloped area that, generally speaking, infiltrates water into the soil more than like roof area, more than pavements. And so anytime a developer in West Virginia does a big project like that, the state has regulations that they have to put in some sort of a way to capture runoff, because you don't want to make flooding any worse than it already is in the streams and other water bodies that receive the runoff. And so they put in storage ponds, and they do kind of a flow over time analysis to find out how big should the pond be. They look at, for a given storm, the hydrograph of runoff, and they also look at the flow rate that they're allowed to release into the stream, and the difference between the two tells you how large the storage needs to be. So that's one of the, two of the real-world applications of Reynolds transport theorem. Before we finish up for today, let's just take a quick look at the key ideas behind one of your homework problems. Okay, we have a tank, and there is one stream in where they have told you the cross-sectional area, but where the velocity is unknown. And then there is a flow out, and they have specified that you should use v equals square root of 2gh. So that means that's an orifice. It looks like there's a container, like a pipe, but then the pipe terminates, and it's just a free flow jet out of there. So the velocity is from the orifice equation. The cross-sectional area is fixed by the diameter of the pipe, and the height of the liquid level is 1 meter. So the cross-sectional area of the tank is given directly. You don't even have to calculate that from a diameter. And they tell you how quickly it's rising. So this is kind of like the reverse of the example we worked in class today, where we were trying to find the velocity of the rise from known in and outs. Here, they give you the liquid level rise, and they give you the out. What you're trying to find is the in. So remember, this is an application of accumulation is in minus out. And if the liquid level is rising, that means there's a positive accumulation. So you can do this one on a volumetric basis. You don't have to do this necessarily mass. You can solve this straight volume. So for the height of 1 meter, you can find the velocity out with the given orifice equation. And then once you have the v out, you'll find the q out. And then the accumulation rate is defined by the rate of rise and the cross-sectional area of the tank. So then q in is what you need to find. And then once that's established, you can find the v in using q equals va. And they already told you a. Any questions about these hints for problem 55? All right, that's it for today. I'll see you next week. Have a good one. Mm-hmm. Yeah.